Okay, welcome back to lesson number 3 of our quadratics unit. Yesterday we looked at incredibly exhilarating, fun method of taking a quadratic function equation that was in general form ax squared plus bx plus c and putting it in vertex form, a method called completing the square. Why do we want to do this? Well, looking at general form, I can't tell what the vertex is. I can't look in and tell what the vertex, where it is. So, but by putting it in vertex form, we can identify HK, the vertex. So we use this method called completing the square, which most of you did not take much of a liking to, and it is a rather heinous process. But it is a necessary process when you get into pre-calculus and get into what are called conic sections and into calculus. So you need to know it. But I did promise you a shortcut, and I always deliver. So, from yesterday, let's pick up a few things that we learned. When we completed the square, part of what we got, the vertex form, from a general form like this, we got this right here, a times the quantity x plus b over 2a squared. Well, if my vertex form is always going to look like this, then I can make a generalization here, a formula, h, the x-coordinate of the vertex. If I have x plus b over 2a, it's x minus h, so it's going to be negative b over 2 times a. Cool, cool? All right, now what about k? Well, keep in mind that k is a y-coordinate, okay? It's a function of x, and my original equation relates y and x, so if I plug in this value here, negative b over 2a, that's an x-coordinate on the parabola. It's at the vertex. So if I plug that into the original function, that'll give me the y-coordinate there. That'll give me k. So k I can write is f of negative b over 2 times a. And shazam, there it is. This is the shortcut to find the vertex. Let's see this formula in action. Here we go. Okay, so look up here, we've got y equal x squared minus 6x plus 10. I want to find the vertex, and I'm going to use a shortcut. So let's see. First thing I want to do is identify A, B, and C. All right, now, H is what I'm going to find first. That's the negative of B over 2 times a, so the negative of negative 6 over 2 times 1, and that comes out to be 6 divided by 2, that comes out to be 3. Pretty easy so far. Now to get k, that's just the y-coordinate that goes with an x-coordinate 3. So I'm just going to take f of 3. Plug it in, let's see. I get 3 squared minus 6 times 3 plus 10. Let's get out our calculator. No, we don't need our calculators. We'll just use our bleeping brains. 9 minus 18 is negative 9 plus 10 is a positive 1. Presto changeo, there's my vertex at 3, 1. Wow, that was quick. Now, one thing that we haven't identified here about our parabola that we did when we put it, when we completed the square, was, is this vertex a maximum or a minimum? Does the parabola open upwards, yielding a minimum, or does it open downwards, yielding a maximum? So how do we do that? That's right, Zach. We look at A. A is positive. And remember we said if A is positive, if you're positive, you're smiling, it opens up. You get a smile. So what we have here it reaches a minimum. Cool, cool? All right. Well, let's have you try one. So let's take a look at h of x is equal to negative 5x squared minus 20x plus 16. Okay, so what I want you to do is take this, use a shortcut to find the vertex. Tell me whether it's a max or a min. Okay, so pause the video right now. Okay, you're back. Let's see how you did. First thing we want to do is identify A, B, and C. Now, to find h, we're going to take the negative of b over 2 times a, and we get positive 20 divided by negative 10. We get negative 2. Do you get that? Yeah, right. Okay, so k, we're going to take, in this case, h of negative 2. Plugging that in, we get negative 5 times negative 2 squared minus 20 times negative 2 plus 16. And let's see, do we need our calculator for this? No, we're accelerated. So let's see, we get negative 20 plus 40 is positive 20 plus 16, that's 36. So we got our vertex, hopefully we got our vertex. I got our vertex to be negative 2, 36. Now, is this going to be a maximum or a minimum? How do you tell? What do you look at? If you said, look at A, you are correct. A is negative, so this guy is going to open down. So this point is a maximum. Now, one thing I want to emphasize here, when we refer to maximum minimums, the maximum value that the function reaches is 36. The y-coordinate, keep in mind, is the function value. The x-coordinate just tells me where it occurs. All right? So we say it reaches a maximum at 36 when x is negative 2. All right? Now, what we're going to do is apply this in a quote real-life situation. Actually, a simplified real-life situation. But we are going to look at it in context. And I've got a problem for you to read. And I'll read it with you. A company projects its profit to be given by the quadratic function p of x equal 48x minus 3x squared, where p is dollars and thousands, and x is the number of units sold. Kind of exciting already. How many units sold will yield a maximum profit? What is the maximum profit? Ooh, it's kind of like a mystery. Getting exciting. So what I want you to do, take this function and see if you can first identify A, B, and C. Find the vertex by the shortcut method. Okay, I will pause here for about 5 minutes. I'll just be standing here for 5 minutes. So you pause the video, and then we'll come back and look at it. Great. Back. Here we go. A, in this case, is negative 3.
Notice that we've got these two terms switched. Some of you who are a little more astute may have rewritten that like this. B is 48, and C is 0. So H, we're going to take the negative of B over 2 times A. So I'm going to take the negative of 48 over 2 times negative 3, and that gives me negative 48 divided by negative 6 comes out to be 8.
Cool, cool, cool. Get the rest of our vertex. K is going to be P of 8. And that's going to be 48 times 8 minus 3 times 8 squared. And I believe that crunches out to be 36. So what does this mean? When H is 8, K is 36, 8 comma 36. Well, remember, this is XP. X is the number of units. So if we sell 8 units of our product, we get not just $36, we get $36,000. Cool, cool. Okay, now, I don't know what we're selling. We sold 8 of them. We got $36,000. Obviously, we're not selling, frisbees, maybe supercomputers or something. Let's kind of make sense of this graphically. Now, we don't know a whole lot about sketching parabolas. But I do know a couple things. X represents the number of units. P represents the profit. I do know, as far as my domain here, I can't sell a negative number of units of whatever it is I'm producing. So my domain must be greater than or equal to 0. And I could refine that because it would have to be whole numbers. Okay, I can't sell a half a unit of whatever I have, I would assume. Okay. Likewise, well, what about profit? Well, profit could be negative, actually. But my starting point is going to be right here. Now, A is negative, negative 3, so it opens downwards. So we get something that looks like this. This parabola, it stops, or actually starts right here at 0, 0. Here is the point that we found, 8, 36. That gives us, that is the point where our profit will be the maximum. Now, one thing we'll be interested in later is finding out this point right here. That point where our profit goes from positive to negative. That point right there, we call him the 0 of the function. That's coming up soon. We'll get there. All right? Okay. Now, let's take a look at another problem. Now, before we can actually attack this problem, we've got to do a little learning here. A little physics learning. When I've got an object that's projected upwards, its height at any time t is given by negative 16 t squared plus v sub naught t plus h sub naught. Oh my gosh, Mr. Clark, what in the heck is that? There's too many variables. No, actually there's the same number of variables we've been using. There's only 2 variables. My independent variable is t, and my dependent variable is h. These are constants right here. This v sub 0, or I call it v sub naught,
What that means is the V stands for velocity, that sub-zero stands for initial or starting. That's the, whatever this object is that's being projected upwards, that's the initial, the starting velocity, the velocity at which it's thrown or whatever, kicked upwards. So V sub naught represents my starting velocity. Well, now, h sub 0 or h sub naught, what does that represent? Well, h represents height, height off the ground of this object. So h sub naught represents the starting height. When the object is projected upwards, what is the height at that time? And we called that at the time we start this, we project this object upwards, we say that's t equals 0. Our experiment starts now. So that's the height when t is 0. Okay. What about the negative 16? Where does that come from? Well, what that has to do with the force of gravity here on Earth. Okay. And we'll talk about this more tomorrow. But as far as we're concerned, as long as we're working on Earth, we're going to be using this constant negative 16. Now, if next week you go to Venus, you're going to have to find a new constant to use, okay? But for right now, we're going to stay here on Earth. So, here's our problem. A slingshot projects a rock straight up with an initial velocity of 100 feet per second from an initial height of 6 feet. At what time will the rock reach its highest point? What is the maximum height? The first thing we want to do is to take our general position function here, our general height function, and write it specific to this problem. So I've got h of t, it's going to be negative 16t squared because we're still on Earth, right? Right. What's my initial velocity? Anyone? 100 t plus initial height, and that's going to be, what was it, 6 feet off the ground. Now, one comment I want to make, generally, we will use t as time in seconds. And height, although we could use different units of measure, we will quite often be using feet. And those of you going on to physics, which is a lot of you, you're going to be looking at this function, and that is quite common, although you will use meters, but quite often you'll use feet in seconds. Now, let's think about this problem graphically like we did our other problem. Our domain variable is t, time. Height is a function of time. So our range variable, our dependent variable, is height. Just like our previous problem, our domain starts at 0. When our experiment starts, that's t equals 0. And it goes to infinity. In this case, it's not just the whole numbers. T, time, is continuous. So I can just write with confidence here, domain is 0 to infinity. Again, it's a parabola, it's quadratic, so I get a parabola. A is negative, so it opens downwards. So I get something that looks like this. Any point on here represents a time and a height. At this point right here, at the vertex, if I find that point, that will give me the time at which it reaches a maximum height. So, let's use the shortcut method to find the vertex. A in this case is going to be negative 16. B is 100. C is 6. So I hate to use HK because I'm using H for something else. So I'm just going to write negative B over 2 times A is going to be, let's see, negative 100 over 2 times negative 16. I get negative 100 over negative 32. Now we're starting to get into some ugly numbers here. So we probably want to take out our handy dandy, what? Now, not a notebook, a calculator. Duh. So we take out our handy dandy calculator, and I get it to be, of course I do this in my head. Yeah, right. About 3.2. We'll round to the nearest tenth. Cool, cool? All right. Now, to get the y-coordinate of the vertex, and I could write k, but I'm starting to get too many different letters in here. So I'm just going to write h of 3.2, and I plug that in here and here, and crunch that out, and it crunches out to be about 162.2. And let's see, what does this mean? That means my vertex is 3.2, 162.2. What does that mean? Keep in mind, first number here, my domain variable is time. And my range variable is height. So that says, after 3.2 seconds, I will have a height of 162.2 feet, and that is the maximum height. Now, I'm not going to give you any problems. I've been giving you a couple of problems to work on, but I want you to think about a couple things. Does that domain I have up there, 0 to infinity, is that actually appropriate? Why or why not? Something a little fishy about it. Secondly, what does this point right here represent as far as our rock? And tied to the first question, what would this point right here mean as far as our rock is concerned? So, see what you can do with those questions. We'll talk about them tomorrow. And till then, I'll be I'll be going off and working some more math problems because that's what I do in my spare time. See ya.